Thank you very much. This has been a very nice conference, so I thank very much the organizers for giving me the opportunity to be here. About the title, I will explain the first line of the title at the end. In the meantime, well, I've been fond of three space problems for a long time. This book is from 1996, so there's a long time on this. And a three space problem means that you have a property and ask if whenever a subspace of a Banach space and the corresponding quotient have that property, if the middle space has the property. In, say, my language, it's not mine, but this, when you have an exact sequence like this, if y has the property and x has the property, if z has the property. The space Z is sometimes called a twisted sum of y and x, so the question is if twisted sums of spaces with some property have the property. From now on, whenever you meet that diagram, an exact sequence means y is a subspace of z, and x is the corresponding quotient z over y. Is the shortest way to say that. So let's think about the three-space problem for the property of being polyhedral or better isomorphically polyhedral, which means a Banach space is polyhedral when every subspace, finite dimensional subspace, or subspace of dimension 2 is enough, is isometric to a subspace of some L-infinity space. Or if you prefer, the unit ball is a polyhedron, a convex hull of a finite number of points, right? This L-infinity n is not necessarily a subspace of X, it's something which is outside. This property is isometric. One of the particularities of thinking in exact sequences, thinking in this way, is that about the space set, you know nothing, except what is in that diagram. I mean, you don't have any representation of the norm. If I give you a Banach space set, admitting a subspace Y, and the quotient is X, you know nothing about the norm of Z, of any description of the norm. So, you cannot think about polyhedrality. You have to think about isomorphic polyhedrality, the property of being isomorphic to a space which is polyhedral. Or you prefer, you can renorm the space to be polyhedral. Right? Examples. C0 is polyhedral, but C, which is isomorphic, is not. It's only isomorphically polyhedral. Spaces of continuous functions on some countable diagonal are isomorphically polyhedral, and if you take the hyperplane of functions with vanish at the end, then there is polyhedral. They subspaces, Schreier spaces, combinatorial spaces, most of them are polyhedral or isomorphically polyhedral, and there are others. There is one Paris, there is one from Kuhnen, there are others. Who knows? Others. So, let's think about the property if Y is isomorphically polyhedral and Z is isomorphically polyhedral, must the middle space Z be isomorphically polyhedral? I thought, no. A counterexample. Probably the simplest, I imagine, could be a counterexample is a twisted sum of two C0 the gamma spaces. Because the simplest polyhedral space we have in mind. Any twisted sum. These twisted sums are some of them which are normal. They are CK spaces obtained out from a almost disjoint family of subsets of N. Sometimes are called Muroka spaces, sometimes are called Nakamura-Kakutani spaces, whichever. These are the normal twisted sums, but there are others. For instance, here in the room, Gregor Pepanek and Alberto Salguero made a twisted sum of 2C0 gamma, which is not isomorphic to a CK space. So there are others. These papers are papers containing some of new results of this type of space. So the question is, must set B, the twisted sum, be isomorphically polyhedral? How do you check that? Another possible example, or counterexample, twisted sums of the spaces of continuous functions on some ordinal, countable ordinal, and C0. From this there exist spaces strangers like this, and the most strangest, which was my candidate to be a counterexample, is a twisted sum in which the space in the middle has the property of the quotient is strictly singular. So the space in the middle is not a Lindenstrauss space, it cannot be renormed to be a Lindenstrauss space. You can think it from your perspective, the space set cannot be renormed to be a Lindenstrauss space, so that the dual is L1, but the dual can be renormed to be L1, because the dual of Z is isomorphic to little 1. So It's exotic in somehow, this space. And these were my candidates to counterexamples. Everything you want to know about these examples is in the book. So whatever you like is there. And now the theorem I wanted to display today. No, they don't work. Why? In each case, for a different peculiarity. In the first case, the way to prove that a Banach space is polyhedral, as Distel said in some pages in his book, Sequential Series Banach Spaces, polyhedral spaces are too difficult, except for Fonf and some collaborators of Fonf. It's too difficult. The best way to handle if a Banach space is polyhedral is through a boundary. If you are able to get a good boundary, then you can prove that the space is polyhedral. The best boundaries so far are boundaries with that property called asterisk, we don't care what it is. A special type of boundary, with some special property. Spaces with that boundary are isomorphically polyhedral up to the point that separable spaces are isomorphically polyhedral if and only if they admit a boundary with that property. Nobody knows if they are equivalent in general. All these type of results is in this paper of Fonf and Pellares, Smith and Trojansky, a beautiful paper containing many results and many details about all this stuff. Now, back to the examples. Blah, 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 we prove it. If you have a twisted sum of C0, C0 gamma, and a Banach space admitting a boundary with the property, additional property asterisk, then the middle space admits a boundary with that property and therefore isomorphic operator, and we are done. The nice part of this is we are able to produce a norm into the middle space. How do we do that? In two steps. First one is drawing a little bit. This is consequence of those beautiful papers of, again, George Plebanek and Alberto Salguero about twisted sums of CK spaces. Then they produce the type of sequence above. L is a compact space, very peculiar. It's the unit ball of the dual up adding, to which we add a discrete set of sites kappa in that case, just that the union is still compact, so the points of kappa accumulate on the ball. The thing is that one can prove that any sequence of C0 and X, no matter which X, can be inserted in a drawing like this. It is strange, but it works. This does not work for others. If you try to put, say, C01 instead of C0 kappa, that fails. There is no version of this for other C kappa spaces, only for C0 kappa. So the first step is to put the sequence inside this diagram, which means that set, actually after norming, is a piece of CFL, exactly this which is here below. Now, once you have this representation of set, then you can define this boundary, prove that the boundary has the property asterisk, the space is isomorphic polyhedral, that's their norming, and that's it. Probably you are stunned, like me, by the 2. This 2 in the right is what makes the proof work. So, in the end, it seems that probably no counterexample of this type exists. This probably means maybe there is an isomorphically polyhedral X without a boundary with property asterisk, something which would be better than this. Maybe the asterisk exists and then could be obtained, maybe. But so far we know today, no. So in this line, probably no counterexample can be obtained. About the other one, well, we proved this. Any twisted sum of space of continuous functions on some countable ordinal and a separable Banach space with a boundary approximation of property has to be isomorphically polyhedral, which is strange. And the proof is just mere drawing. I draw, which is the only thing I can do. I draw until the end. What do I draw? Yes. First, continue. I put the simplest case for the sake of this conference, right? Instead of omega big ordinal, I put omega power omega. So see, continuous functions on omega omega is the C0 sum of continuous functions on omega n. In general, continuous functions on a sequence of ordinals converging to the limit ordinal you are dealing with. Then, take the projection onto the end piece, draw a little bit. You have to learn to draw, but if you learn to draw, then the sequence below exists. It's a twisted sum of C and the piece, or less a piece of the previous one, and you have this sequence. Now take this sequence below, take all these sequences below, and amalgamate above. Right? I make the C0 past of all these things. And below, I put the sequence I had from the beginning. Now at this moment, I have to move to a different place. In papers time ago with Yolanda Moreno, we developed something that we call the chasing device. Chasing device is thinking about the sub-6 theorem or injective Banach spaces and think like this. I draw for you. This is the subspace and this is the quotient, right? If the subspace is, say, L infinity, no matter which quotient you put, the sequence splits. I mean, this is complemented into the middle space. If this is C0, well, then this has to be separable. Okay. So the idea is the splitting of the sequence, the fact that this is complemented, depends on a balance between the properties of the subspace and of the quotient. This is the idea. In this case we have here, which has some little trick. The additional property we need to make this sequence good means split, or we do what we want to do, is the bounded approximation property. So in this case, only in this case, the proof in general is a little bit more complicated, but in this case, every twisted sum of X and this space, which actually is C0, since X is separable, splits. Okay, then to make the sequence, the whole passing sequence split, we need some additional property of X, which is the bounded approximation property. That's the essence of the proof. Now, in general, when other ordinals here, omega, omega, omega n, you don't have that the sequence below splits. You have less. Then, what you get with this trick is that the sequence below can be embedded into the sequence above through some maps. I mean, the map yn can be extended to a map from Z into the middle sum. This is what I can do using this chasing device. Once we get to this diagram, the rest is pure joy. The space Z is a subspace of this product. This product is isomorphically polyhedral, so your space is isomorphically polyhedral. That's it. Mere drawing. This means, again, that probably no counterexample of this type exists. Probably means maybe there is one Banach space without the bounded approximation property. You can put maybe, but not in the regular world. So we don't have examples of one type or the other type. So, sorry, but I run out from candidates to counterexample. I don't know where to look for a counterexample. And worse than that, and this is the reason of the title of limits, worse than that. Even if I had example in front of me, even that, I don't know how to recognize it. Because this type of spaces have, this is the property they have, and I'm then interested in the first one, as saturated by copies of C0. This is a theorem, well, the isomorphically polyhedral part is a theorem of Thomp. An isomorphically polyhedral Banach space is C0 saturated, the copies of C0. And nobody, as I know, except Leung, Denis Leung, is able to distinguish between C0 saturated and isomorphically polyhedral. Leung is able because he had a counterexample, he made one of a C0 saturated Orlik-like space, which is not isomorphically polyhedral. But outside that, it's too complicated. So even if I had an example, I couldn't know how to prove it. So I'm stuck. And this is a problem for me because I wanted this problem, I wanted to do something, but nowadays I don't have a reasonable candidate to counterexample, and I don't have a reasonable candidate to a way to a proof. I'm stuck. I'm begging help. So, well, these are the papers in which these ideas are contained, more or less. Thank you very much.